speaker today. We have Hooman with us, who's joining us from Kyoto University. Hooman's a postdoctoral researcher there who's working on taking robots out of the lab and into the real world with the goal of improving HRI. Uh, his passion lies in designing algorithms as well as new robots that can bridge the communication gap between humans and the robots. And before joining the university, he was a postdoc researcher at University of North Carolina in the United States and completed his Ph.D. at the University of Colorado Boulder. Uh, and his dissertation was focused on understanding how robots can participate in conversational groups and learn about the physical aspects of people within the group. Uh, Thanks for joining us, Human, and agreeing to present about your research. And I'll let you start sharing your screen.
So thank you so much for having me. And I'm going to talk a little bit about the past 7 years that I was doing in a variety of organization and talking about the problems that I faced. Before I start, a little bit of myself. I finished my PhD at University of Colorado Boulder, and then I did a postdoc at UNC Chapel Hill, and now I'm doing a postdoc at Kyoto University. My vision of the future is that we have the robots everywhere. The robots are going to have conversation with us. They are going to teach us new skills. They're going to help us do our groceries. They are giving us directions, and they are going to be a good companion for us. But where are these robots now? If you look at the current state of the art for human-robot interaction, you will find out something like this video on the left. And as you see, the robot is in the way of the police officer, or if we have a robot having conversation, then we are seeing like some scared look like the woman. What are the problems and how we can achieve a good human-robot interaction? So one of the problems is the perception mismatch. And it means that the way that we see the world, sometimes it's completely different from the world that the robot sees. So our states of the world sometimes are not the same. And the problem happens in every communication, in every interaction with a human. We are having some information loss. Let me give you an example. There is a children game named Telephone, and it is an information loss game. And basically, it's go like the first person select the word, and then it passes to the next person. It goes to the next person, and at the end, we have a dramatical information loss during those interactions. I'm going to show you a video of people playing this game. So the first word or the word that we are going to say is like riding a motorbike. So it passed to the first person, and the only the objective is to do the same and convey to the next person. So you get the idea of the game. Now I'm going to fast forward it, and let's see what happens at the end. So this is something that happens when we are communicating with each other. So I believe that for a better human-robot interaction, we need to design robots that convey information to the human in a better way, in a more coherent way, and with less information loss. And also, we need to design robots that can understand the human's behavior and they can predict it. The first direction of my work is designing robots that convey information to the user. And for this, I first look at what type of information should be conveyed to the user. For this one, we show a video of people interacting with three different robots, an aerial robot, a giant, like a big robot, and also a small ground robot. And then we ask them that during this interaction, what type of information is necessary for you to know in order to finish your task or feeling more comfortable. So the takeaway of this work is that we have a priority list that we know what type of information users need to know. The second body of work is that using new technologies to convey the existing information, the information that we find out in our first study. So the idea here is that is there a possibility of showing the state of the world in an easier way, and also in a way that we have less information loss to the user. So we use augmented reality for doing it. During the three projects that we've done, we show the intention of the robot to the user through a Microsoft HoloLens. So as you see here, the robot shows where it is going, or in this project, it shows the camera feed of the robot on top of the robot. Or in the other project, we used augmented reality for showing what the current input do to the robot. So, for example, here the user or the teleoperator, instead of controlling only the robot, it can control an augmented reality version of the robot, and the robot follows it. And this shows, this one and past two projects shows that showing information in this way reduce the mental workload of the user. It reduce the number of crashes and increase the usability of the system. And last, I look at the exploring possible informations to convey. And by that, we look at what is the limits of the information that we can convey. So, for example, can we convey affection? Is there, can we build a robot that can show affection to the user? For this one, we make a hug bot, a robot that can hug people. So we first study that how people hug each other. Then through using soft robotics, we made a soft actuator that can do the same type of pressure and same type of so to say, hug to the user. And the result was that we put this into the giant panda bear, and we find out that especially children love this type of robots. The second project was that, can we convey emotion? Can we kind of show that robot feels scared or frightened, and can we convey this type of information to the user? So we've done it by looking at expandable structures, and we wanted to make a robot that can increase its size to show that it is dangerous. So like the pufferfish and some type of animals that do it in the bot. So when the user goes close to the robot, it pop up and can convey this information that don't come close to me, I'm dangerous. The next project was to convey awareness. So right now, with people using virtual reality glasses, they are kind of isolated from the real world. So the idea here is that if a user wearing a virtual reality glasses and think that see a chair in the virtual world and want to interact with it, can we make a robot that realize that and try to convey that awareness that like there is a user thinks there is a chair here, so I'm going to bring a chair so the user can interact with it. And that one was through an expandable structure too on Roomba. And these swarm of robots can manipulate the environment to convey awareness to the user. So, for example, here the user is in a room with walls, but as it moves, he can like touch the walls, or like here can interact with the objects in the virtual world. So all of the projects that I show you mainly focused on designing robots that could convey information to the user. For the second part of the projects that I'm going to show you, we are focusing on designing robots that can understand humans better and also can predict them better. For this set of projects, I focused on conversational group. And the reason that I focus on conversational group was that I find out so many interesting real world problems that I wanted to solve. So the problem with conversational group is that we still don't know many things about it. So as an example, if a user wants to like go close to the robot, at which moment the robot knows that the user wants to talk with the robot and not just passing by. So this is like only one of the still like this problem is not fully solved. But when we have multiple people that interacting with a robot, the problem will be even harder. So the set of problems that I tried to solve was not only by looking at the literature reviews. I had a chance to work with two robots. First, direction robot at Microsoft Research, which was capable of
Can I help you find something?
direction to the user.
What room number are you looking for?
Conference room 3800.
To get to conference room 3800, go to the end of this hallway. Turn right and go straight down the hallway for a bit. Conference room 3800 will be the first room on your right.
Thank you.
And the second robot that I had the chance to work with was the character robot at Disney Research. And by looking at the problem, the existing problem when people interacting with these two robots, I find out that we're still at our early stage of understanding conversational groups and detecting them, and the set of challenges that exist there. So the contribution to this set of problems was first I made a couple of data sets, then I tried to compare the information, and for now just ignore the word formations and think it as a conversational group, and I will describe it later in my slide. So I compared the conversational group between and then find out the different characteristic of it, and then I try to detect the formations for conversational group, and then I try to bring more characterization and to describe different formations. And then we tried to detect the missing people in a conversational group, and also identifying the group attention, focus of attention in conversational groups. So the idea of a formation already hard-coded in your brain. If I show this picture to you and ask you to tell me which people are in a conversation with each other, you can easily do that. So let's give it a try. So probably you find this formation of size 8, this formations of size 4, size 3, size 2, and that is it. For the sake of completeness, the definition of a formation by Kendon is a formation arises whenever two or more people sustain in a spatial and orientational relationship in which the space between them is one to which they have equal, direct, and exclusive access. But whenever you heard of a formation, you can just think about conversational group. So a formation appear in different arrangements. So whenever we have more than two people, usually the most of time the formation comes with circular arrangement. But when we have like two people, and sometimes more than two people, but majority of time two people, we have L arrangement, vis-a-vis arrangement, and side-by-side arrangement. And each of these formations give an idea about the interaction happening in the in the conversational group. For example, when people tend to stay side by side, it means that they are sharing a resource like a map, or they are looking at an artifact like a painting in a museum. So the first contribution was to create some data sets to study formations. So at Disney Research, we made just a mean data set. In Colorado Boulder Atlas Institute, we create a Babel data set. And Babel consists of 45 minutes of people interacting with each other in a conversational group of different size, and try to arrange different type of formations. And you can access the data set in the link you see. And finally, it was a HRI proof of concept data set, which was an human robot conversational group data set. And the takeaway here is that now I have access to human-human and human-robot data sets that I can use for analyzing and testing. The second contribution is that comparing human-human conversational group with human-robot conversational group. So I just go really fast that we find out that human-robot conversational group is different from human-human conversational group, but we can easily convert them with each other. So with a factor in our study, we can use our knowledge of human-human interaction and convert it to human-robot conversational groups. And so, for example, people tend to stay closer when they're working with a robot compared to human-human conversational group. So, and then although the takeaway here is that people tend to stay closer, but the relative angles are going to be the same. I'm going to jump through the detection of a formation and also characterization, and focus on the last two projects that I've done. The first one is detecting missing people, which was published at HRI 2022. And the idea here is that if we have a conversational group with a human, with a robot, and one of the participants start a conversation, so start talking with a robot, what happens inside the robot is that a robot has sensors, and then the information of the sensors goes to human detection algorithms, and then the human detection algorithms go on a formation detection algorithms, and then based on that we have an interaction engine that decide what behavior should the robot do, and all combination of these components lead into a robot's action. And based on that, the robot respond to the participant. The problem is that these three components, sensors, human detection, and group detections, are not always 100% accurate. So, and faulty sensor information led to wrong human detection, and also the group detection does not work. In that case, what we see is that it is going to be distracting for the interaction. So the two problem that might happen is that, for example, if the group detection does not work, and we have person come close to the robot, and the information detection algorithm, instead of like 3 people in the conversational group, detects the newcomer, then the robot's action might be faulty, and for example, there might be privacy issues here. Or the other problem is detecting less. So, for example, the robot, the participants ask a question from the robot or interact with the robot, but because of the faulty group detection algorithm, the robot ignore that request, and also it leads to a wrong robot action. So this is the problem that we try to solve. Our method is, and then the question that we are asking is that although we have a faulty group detection algorithm, is there any way that we can assume that there is a person over there, and with faulty group detection, we had the right robot action? For example, the robot take a more conservative approach and also ask for clarification. For example, come closer, or I cannot see you. So for doing this, we first compare the formation of the same size. For example, we went through all our data set and select the same information of same size, and then by finding like a random person in each formation, we try to overlay all the formations on top of each other. For example, for these two, we try to overlay all the formation on top of each other. As a result, we saw that based on the 3 data set, we find out that people tend to stay on predefined location in the conversational group, and with respect to a position of one person. So using this information, we make a classifier, and the classifier knows the can predict the position of the people in the conversational group. For example, right now everyone is staying on the predicted position, but when a newcomer comes, then people tend to shift a little bit to be more welcoming. And with this, the robot knows that the location of the people that it detected are not matched with the information size that it think it is. So it can say that, oh, maybe there is like 5 people in this conversational group and not 4. We trained and tested our model on a Salsa dataset and Babel dataset, and the result shows that this classifier is reliable for detecting the missing people in an formation. And the reason that the Salsa dataset is a little bit noisy here is that, as you see here, the Salsa dataset itself has a little bit like a noise compared to the Babel dataset. So I'm going to show you a video of implementation of that. So all the people that you see here are wearing reflective markers, so the robot can see all the people in the scene. And a newcomer comes, and she doesn't wearing like any hats, so the robot does not know. But because of the shifting in position of the people in the conversational group, the robot can detect the position of undetected person in the conversational group. So the takeaway here is that we can detect the error in information detection pipeline, and we can plan for it. The last contribution that I'm going to talk about is identifying the focus of attention in conversational groups. I'm going to start with a video that and show a robot that technically not using camera or a microphone array, and still can detect the focus of attention in a conversational group.
So probably don't want to hear that. Another one that got ruined for me was McDonald's fries. They are not vegetarian. How? They put beef like spray on the fries, or some sort of like.
And as you see, when the turn taking happened, the robot correctly predicted the person who is talking, and as a way to show that detection, look at that active speaker or the focus of attention. So for identifying the focus of attention or group attention point, the state-of-the-art algorithms are looking at either using a vision base and looking at who is the whose mouse is like moving and probably is the active speaker, and look at visual cues, or it looks at audio cues. And the audio cues with microphone array has a problem that if we are in a noisy place or a person who is like louder are in the space, it is going to result in the faulty detection. So the observation that we had was that when someone starts talking, the people in the conversational group tends to shift their gaze toward the focal of attention in the conversational group. So using this observation, we come with two approaches. The first one is a naive approach, and the naive approach uses the gaze and the head orientation of people in the scene, and based on the voting scheme, it detects the person who the majority of like head orientations select the person who is the closest to the majority of head orientations, and detect that person as a focus of attention. The second approach is a hidden markup model, and for doing so, we first give a initial state to all the people in the conversational group, and then we had an observation. For example, given these head orientation, we try to calculate the different angle between the gaze and each person in the conversational group, and we create a normal distribution for that. For example, when the different angle is larger, it means that it is less probable that that person is talking. By having a set of observation and by set of gaze ray or head orientation, we try to calculate that what is the probability of person I is talking given this observation. And after that, because we were looking at time series, we try to calculate that what is the probability of someone talking given the states of previous point in our conversation. And after that, we try to maximize the p-value, and we detect the person who has the highest probability. I'm going to give you 3 videos of implementation of the system. So this is the first one.
Yeah, I've heard some about that.
A lot of time. Yeah, so I've been to several national parks already.
Ooh, which ones?
The Zion National Park, the Bryce Canyon, the Olympic, and what is the one? Mount Rainier.
Oh, yeah.
And of course, Rocky Mountain.
The second video that I'm showing is that most of the time in a conversational group, focus of attention is a person in a group. But in this case, I am bringing a poster that I haven't told anything about it to the participants. And as I bring it, people are confused, and then they try to look at that poster. And because of that, the robot looks at that poster. And then after a while, they lost their attention, and the robot knows that and go back to the conversation. What is interesting is that even this approach works with 2 people. And as you see here,
The other problem, like, how long does it take to grow?
A few weeks.
Oh, okay, that's not bad. Oh, you could have like a new bench every like month.
New bench
That'd be
every
cool.
month.
You could only really sit on it for like the last
So
week.
I've actually
but-
been thinking about that a lot. I just read a few papers where they had a ton of like foam prototyping. I forget the name, but you know how people take blocks of
very
foam and
interesting
like,
because when we have 2 people and each person are talking like their gaze is like directed to the other person, it makes it hard for the algorithm to detect it. And but interestingly, we find out that the algorithm is working here. And the reason is that the active speaker tend to have a head movement and try to like look around. But the person who is just listening constantly looking at the speaker's face. And then that is the reason that our approach work in this scenario too. So the takeaway here is that the HHM model can detect group attention point or focus of attention, and can help the robot to act normal here in these scenarios. With that said, I talk about the contribution on making algorithms that can help detect deformation or detect the possible error in the formation detection algorithms, and also try to understand the human dynamics better. So the final takeaway from this section is that we have the data set for the community. We understand the difference between human-human and human-robot interaction conversational group. And then we can detect formations, and then we can also detect the possible inaccuracies and plan for it. And also we can detect the group attention project. And this was focusing on the conversational group in order to achieve my vision of having the robots everywhere. And that is the second part of it, and designing robots that can understand humans' behavior and human dynamics better and plan for it. I want to thank all my collaborators for all these projects, and also I want to thank all the artists and videographers that helps with the amazing footage for this talk. And thank you so much for listening. And if you have any question, please email me. And with that said, I'm done, and then I'm happy to take any question here.
So thanks a lot, Hooman. It was really interesting. First question, I have several of them, so maybe if somebody has another question, should interrupt. First question is whether I can reuse this if I want to replicate this behavior on a robot I work on. How should I start?
Yeah, so basically, it depends on which part of the which project are you referring to? But so for the past project, we open sourced the code, and it is on the GitHub. And that is like one of the available codes over there. And then the data sets are the data set is also available, and the rest of it, it is like if you send me an email, and then we can talk, and like I can like find the codes and like share it with you if you need it.
Thanks. So the next question, unless somebody has another one. You were talking about the noise coming from other voices in a crowded area. And I wondered what is the state of the art on sound source localization, you know, to filter out these external voices using a microphone arrays. I wonder.
Yeah, that's
how mature is it? It is.
Yeah, that's a great question. I believe that with the state of the art for sound detection, I was looking. I don't know that like the signal processing like field is the field that I have a limited knowledge of it, and then I don't know exactly what is the state of the art for noise canceling. But what when I was doing those projects, I was looking at the couple of robots that already using, for example, I know I work with like Pepper. I work with like a couple of other robots. And then I find out that most of time when someone is having an interaction, and then like there is the door of the lab is opens, or like someone comes, the robots like look at that direction and then stay in that direction. So which was very distracting for the interaction. And moreover, for the robots in amusement park with like lots of people, and then it's a noisy area. That is, I know that the robots that deployed to those type of environments is doing poorly. And so it was a long question, long answer to your question. That I was with our approach, we were thinking that it can be used as a so majority of time maybe visual or audio cues is enough, but this can be another component on top of those that can detect when those visual cue and audio cues are not good enough.
And then maybe last question for me. How about moving the robots also, to accompany the formations when somebody comes along? Are you trying to go further in that direction, or what are your current subjects, the next things we're going to do?
Yes, that's a interesting question. So nowadays I'm not like a formation is almost like whenever we have a social robot, we have the concept of the formation. But when I was working during my PhD, and then this is sometimes happening in the field, that most of our at least like my work was a lab experiment, and we were isolating from the real world, and then we kind of like orchestrate the perfect scenario. Nowadays, I'm working with the problem that what happens if we bring a robot and put it in the shopping mall or into the wild, and then like what type of interaction do we expect, or how people are interacting with it. So it is less moving forward for the formation, but it is focusing on this idea of that if we have a robot and put it like right now in the social environment, what type of interaction do we have, and then like how we can facilitate that type of interactions.
Okay, thanks for the talk. It was very interesting. So my question is more in regard to the first part, where you were more focused on the robot communicating to the human.
Mm-hmm.
So forgive me if I already forgot a little bit, because now the second part is more prominent. But
sure.
So if I understood correctly, you build robots with a specific intention of conveying, for example, emotion, or also like don't come near me. And the short question: are you still working in this direction, or is this more like past work?
So I am not like at least for this year, I'm not actively like working on any design problems right now. And but do I still like working on those like ideas? Yes, that is like so like as I explained in the talk, like half of me is like a designer that like to prototype, like to design like new robots that kind of and then like exploring the design space of human robot interaction, and then like and the other side is like algorithmic thinking person that try to like mathematically models the human robot interaction. So I am working on like I have two projects that's still like not finished yet, but I'm working on those areas too.
Okay, cool. And the second question is more, there you were like building more specific robots, and could you think of like takeaway messages that you learned from like this specifically built robots that could be implemented with humanoid robots or like typical robots that are used in human robot interaction experiments?
Sorry, I missed the first part of your question. So can you repeat it one more time? Sorry.
Yes. So for these experiments, for each experiment for one specific type, like conveying emotion, you build one robot that is like specifically designed for that task to do that one. And what are your takeaway messages in these robots that could be implemented with more general robots, like humanoid robots, but the robots that are typically used in HRI?
That's a very good question. I want to so first of all, I don't think that like if we can design a robot, as a designer, I'm saying that if we design a humanoid robot, there is like a set of trade-offs. So if we have a humanoid robot, we are by making a humanoid robot, we are dictating some type of like expectation and limitation to the user's point of view. So for example, if it is a human robot, then like all the people are trying to like talk with the robot, and then not use any type of like other type of communication, because they're expected to for doing so. Or if we have a humanoid robot, then people tend that this is like more intelligent than the other type of robot, so they expected more about it. On the other side of that non-humanoid robots, I'm like what's make me interested in that field is that we are not perfect. So there was a study that it interviewed children with disabilities, and then the specifically the children who lost their arm, their legs, and then they were asking that what type of like prostheses do they want. So interestingly, the people, like the children, were saying that, oh, I want to like my arm longer than the other one. In this case, I can like reach the glass like more easily, or I can like grab the remote control. So and that was an interesting idea, that if we can make something, it's better to like we have more creativity on making, and then maybe like even like the functionality of those designs are better than humanoid robots. So there is like a trade-off that it depends on what you want to do. You can like consider that, do you want to go with something that everyone like expect, or you want to like improve like a couple of like design and like make something a little bit unique yeah. And regarding that specifically about your question, what we can learn to convey to humanoid robots, I believe that it is hard to answer that question, and then the reason is that I don't have enough data to back up my claims, because it didn't designed for humanoid robots. So but I believe that based on my studies and what I can like back it up, is that people tend to like the robots that have more emotions. Like the moment we have like a drone, and then the moment that we put like a expandable structure on top of it, it's kind of like give it like a personality, and then like people tend to like feel attached, not like totally attached, but like at least a little bit. Or when a robot can like hug, although they know that, oh, this is a robot, this is like just like a bunch of like motors that like open and close, but this is like people like the interaction, and they want to try, they want to test it, they want to like have it. That is like maybe the one of the things that I can say that we can learn from my experiment, and then like kind of like have it in the humanoid robots.
Okay, thank you. Very cool. Very cool.
Yeah.
Hey, thank you all. That was a good discussion. And thanks again, Hooman, for presenting your research, and the participants for joining. I think in the interest of time, we'll end the discussions, but if you have more questions, you can reach out to Hooman, as he had mentioned earlier, through email, or you're also welcome to join the Slack channel of Talking Robotics and continue your discussions there. And yeah, thanks for joining, and I'll see you all in a future session of Talking Robotics. Have a good day. Bye.